Okay, so this is the exercise class 4 of Physics 3041. So I assume that you have already gone through the problem set and also uh, the problem we are going to solve in this exercise class. So I'm not going to repeat and rephrase the problem. So let's directly go into this problem. So if I think some of you might think that the information is insufficient from the problem. So the first thing we need to do in terms of solving physics problem is that draw a diagram of the configuration as shown in this slide. Also, this is included in the problem set in the PDF. So the first thing, after we draw down the diagram, we need to put it in some appropriate coordinate. So in this case, I use the something like polar coordinate, but indeed it is not exactly the polar coordinate. So the vertical blue line here just show a line that perpendicular with the horizontal line here. Then the problem, we need to first solve the potential everywhere. So we assume that we need to work out the potential at point P. So as shown here, I use a red arrow to represent the location of the point P. So the distance of the point P to the origin is labeled as R, and the angle between the vertical blue line and the red arrow is theta, in this gray line represented. Also, from the problem, we know that there is a particular charge Q located here. So again, we need to work out some label to locate this point charge Q. So in my case, I assume that the location, the distance between the point charge Q to the origin of my coordinate O is D, and the angle between this black dashed line and the vertical blue line is alpha here. And so note that this this ground conductor with a potential 0 and is a perfect conductor, so it is obvious that this charge would induce image charges in different locations. So from the hint of this problem, we note that there are 3 image charges would be introduced. So the first one is denoted as Q prime, located inside this sphere. And the second one is trivial, that because this is an infinite ground plane conductor, so all we need to do is just flip the whole system through this axis. So I mirrored this point charge Q to the down here and denote it as Q double prime. And also note that the image charge can also be mirrored. That means the image charge can also induce a new image charges. So again, I mirrored this Q prime down to this Q triple prime here. And note that the distance between the origin and this image charge Q prime is denoted as D prime. So after all this notation, we can move on and try to write down the potential. So again, um, we need to first work out the magnitude of some variables. For example, we've already know that the Q double prime is actually the image charge directly induced by Q. So Q double prime is actually equals to minus Q. And so as the case in Q triple prime, as this is a mirrored charge from Q prime. So the rest of the problem is how do we determine the Q prime and also the D prime here. So I'm not going to show you the details how I obtained Q prime and D prime, as this is part of your problem set. So once you work out the image charge inside the ground sphere, then you will work out the charge of the image charge and also the location of the image charge. So for equation 2 and 4, please refer to your problem set. So once we know all the point charge, the charge of the magnitude and also their locations, then actually we can write down the electric potential straightforwardly. So so we just simply apply the cosine law, and then we can write down the potential induced by point charge Q, image charge Q double prime, and the rest of the image charge Q prime and Q triple prime. Recall that this is the original charge, and Q double prime is the mirrored charge directly from Q. So you might already notice that the plus minus sign is changed from the upper expression and the lower expression. So this is, however, this is not the end of this problem, as we need to substitute all these variables, for example, Q double prime and D prime. So once you substitute all the things you know in previous slides, then you will work out this expression. So this is the electric potential of this particular configuration. Okay, so although the expression is a little bit complicated, but the process is straightforward. So the next question is that assume that the charge Q is right above the hemispherical bump. So what is the force on Q? In my defined coordinate, if the charge is right above the hemispherical bump, then this is equivalent to theta equals to alpha equals to 0. So so from the figure, you can see that if theta and alpha equals to 0, then the point charge Q will be placed on the blue vertical line. However, we can ignore the point P here, as the problem now is to focus on the force acting to the point charge Q directly. So it is easy to work out from Coulomb's law directly. So for the first, we know that the Q double prime and Q has the distance between them is 2z. Note that here, I skipped some of the steps. Let me explain the notation here. Fz represents the z direction of the force, because now the charge is located on the blue vertical line. So only thing we need to care is along the z direction. That means the upper direction. And also the only variables depends on the only dependence is, of course, the distance of the location of point charge Q. So I denote it as Z, represent the locations between the origin and the point charge Q. So it is easy to see that for the force from Q double prime, it is the distance between them is 2z squared, and then we need to square it, so it becomes 4z squared. And then Q double prime equal to minus Q, so there comes out a minus sign and Q squared, and so on and so off. Work out all the force induced by different image charge and sum them up. So again, you obtain an expression of force acting on this particular point charge Q. So the Q3 is asking that how much work we need to bring Q in from infinity. So we call that we can work out the work done with this integration, that the force dot the path dot dl, and then from the initiate location and to final location. So as now the problem is only related to z direction, so we can further simplify the integrations into this following form, as shown in equation 18. So if you put the result in A2 directly into this integration, you may find that the integration is quite complicated, that it is not easy to work out analytically. So that's why in this problem, I designed to express your answer in integral form. That means you don't need to explicitly integrate it all. So up to here, this is the final answer. Okay, so in real life, in a lot of physical application, most of the time the integration cannot be worked out even analytically. So in terms of understanding its physics, it is more important to know the method more than the math of how to work it out. So let me recap the main routines to work out this problem. So first, once you have your problem in hand, put it in an appropriate coordinate and define the variables that help you. And then for this image charge problem, the first thing you need to do is to identify all the image charges. In this problem, there are 3 image charges. So once you work out all the image charges, then you can directly sum them up with as the electrostatic solution can be superposition. So you just need to add all the potential one by one. And then also, once you know all the location of the image charges, you can straightforwardly work out the force acting on the point charge Q. And then with the integration, you can work out the work done you need to bring Q in from infinity. So I hope this exercise class can help you with your problem set 4. So see you